All right, so today we're going to talk about the remainder theorem and factor theorem. So as a warm-up, we're going to use synthetic division to divide x cubed minus 2x squared minus 4x plus 5 divided by x minus 3. So synthetic division, that was the one where you set up this box, and inside of that box it has everything to do with this guy, but it's not the negative 3 that you see. X minus 3 equals 0. So we actually use positive 3 right there. Okay, and then set up your line. What goes here are your coefficients. Before you do all those coefficients, let's make sure that all of those coefficients can be written and we don't need to insert any zeros. So if I look at the degree of 3 here, and then I see a degree of 2, I see a degree of 1, and I see just a plain number. So that's good. Everything's represented that should be represented. All right, so the rest of the setup, I'm going to put the coefficient of 1, negative 2, negative 4, and 5. So 1, negative 2, negative 4, and 5. Bring down the 1, and I like to put a plus sign right here. All right, so 3 times 1 is 3. Negative 2 plus 3 is 1. 3 times 1 is 3. Negative 4 plus 3 is negative 1. And lastly, 3 times negative 1 is negative 3. 5 plus negative 3 is 2. Where the 2 is, put an R. That's the right-hand side. R for right and remainder. Number x and x squared. So our answer is, I'm not going to be able to fit it in that space, x squared plus x minus 1 plus 2, and we put the remainder over x minus 3, that original divisor. Okay? What we're talking a lot about today is going to be the remainder. So let's write here, the remainder is 2. All right. Whoa, I didn't know I could do that. All right, so I could show you how to check your work. We didn't do this in class. It's just really unnecessary. What we're talking about doesn't really have very much to do with this. Instead, I want to spend a lot of time about the actual two theorems we're learning today, which is the factor theorem and the remainder theorem. So in order to do the factor theorem, let's think about numbers. If I ask you what 15 divided by 3 is, well, I mean, you wouldn't really have to do this, but if I did, I would do 15 divided by 3 is 5. 5 times 3 is 15. You get no remainder. So you just would say 5, and that's it. Therefore, we would consider 3 a factor of 15 because 3 times 5 equals 15. These guys, once we divided by 3, we got 5 with nothing left over. That's what a factor is. So yes, it is a factor, and the main reason is because the remainder was 0. When you get a 0 remainder, that means that it's a factor. All right? So if I do 15 divided by 4, so now I would probably have to do this. We get 3 here, that's 12, 3. So there's nothing left to bring down. So this would be called the remainder. If you actually wanted to know what it was, remember we would say it's 3 and 3 over the divisor was 4, 3 3/4. But that's really not what we're talking about today. What we're talking about is the fact that because there's this remainder, you would say that 4 is not a factor of 15. So no, because there is a remainder. Okay, so this idea, if you really understand it with the numbers, it's the same exact idea with polynomials. If you go through your division and you get a remainder of 0, that means it's a factor. And if you get anything besides 0, that means it's not a factor. So that's what this is saying right here. So when you divide by when you divide, if you get a remainder of 0, then it is a factor. So if we go back to the top, if we think about what happened at the top, we ended up with a remainder of 2. Therefore, was that an example of a factor? And we would say, no, it wasn't. And that was because the remainder was not 0, or you can say remainder of 2. Okay? This conclusion is known as the factor theorem. Okay? So, we also have another theorem we're going to talk about today. That's it for the factor theorem. It's pretty straightforward. It's just get a remainder of 0, it's yes. Get a remainder other than 0, anything else, it's no, not a factor, okay? The other theorem we're going to talk about is called the remainder theorem. And what the remainder theorem is it's really just a shortcut. So I'm going to rewrite the warm-up. We're still using this warm-up as an example. So x cubed minus 2x squared minus 4x plus 5. So that was, I'm just going to rewrite it so I don't have to keep going back and forth. F of x equals x cubed minus 2x squared minus 4x plus 5. Dang it, I keep forgetting. Minus 4x plus 5. All right. Okay, so what we're trying to show right now is let's evaluate our function at 3. First of all, what I want to talk about is in our warm-up, keep in mind that what we did was we divided by x minus 3. So this 3 is coming from that divisor. It's kind of like what we put in the box up here, is we didn't put in exactly that number. You solved it for 0, so we used positive 3. So it's the same thing here. You're using the 3 because x minus 3 equals 0 tells you to use 3. All right, so let's evaluate our function at 3. So that's 3 cubed minus 2 times 3 squared minus 4 times 3 plus 5. So 3 cubed is 27. 3 squared is 9. So, and then 9 times 2, that's going to be 18. So minus 18, minus 12, plus 5. Okay, so if you add this, 27 minus 18 is 9, minus 12 is negative 3, add 5 is 2. So equals 2. So if you notice, remember that from the warm-up, f of x equals 3. I'm sorry, f of x equals 2. 2 was the answer that we got for the remainder. That is not a coincidence. That is going to happen. That's actually what the remainder theorem is that if you plug in the function of your divisor, then whatever it comes out to be is going to be the remainder. Okay, so as a quick recap, since I got a remainder of 2 here, since the remainder is 2, and it's not 0, that's really the point. Doesn't matter what the number is, but if it's not 0, then we can conclude that that divisor, x minus 3, is not a factor of f of x. So I'm talking about this f of x here. Okay, so let's do some examples on the back. All right, so I want you to find the remainder when 3x to the 4th minus 8x squared plus 11x plus 1 is divided by x plus 2. So remember, we're going to use our shortcut. This is what this is stating. The remainder theorem is just a shortcut. If you want to plug in the c value here, so notice that they're already they're showing you x minus c. But if you set x minus c equal to 0, you would just be using c, and so that's what they showed you right here, is that you're just really plugging in the solved version of the divisor. Okay, so in example 1a, x plus 2 is the divisor, so I'm going to say x plus 2 equals 0, I'm going to use negative 2. So I'm going to evaluate my function. This is my function, evaluated at negative 2. So 3 times negative 2 to the 4th minus 8 times negative 2 squared plus 11 times negative 2 plus 1. All right, negative 2 to the 4th. So if you don't know what that is, take a minute to pause the video, get what that is. You should find that that's 16. Okay, and we do still have that 3 here. All right, now I've got minus 8. Negative 2 squared, that's positive 4. And I'm just going to rewrite all of this. I'm not really multiplying right now. All I did in that step was I applied those exponents, applying the exponent of 4 and applying the exponent of 2. Now I'm going to multiply. So when I multiply, 3 times 16 is 48, minus 32, minus 22, plus 1. So 48 minus 32 is 16, minus 22 is negative 6, plus 5, or plus 1 is negative 5. So to answer the question, really the question is not so much about the remainder, but it's about, is that a factor? So since when I used x plus 2 as a factor, so really using negative 2, right? When I used that as a factor, I got that the remainder is negative 5. So the remainder theorem would tell us, no, that is not a factor. And the reason is because there is a remainder of negative 5. Or really more importantly, the remainder is not equal to 0. Okay? All right, so why don't you pause the video, see if you can do B on your own, and then I'll go ahead and start. So f of 3 is 3 cubed minus 4 times 3 squared plus 2 times 3 plus 3 is 27. That makes 9 times 4 is 36 plus 6 plus 3. And if you do all that, you do get 0. So we would say, yes, this is a factor because the remainder is 0. Okay, now question C. I want us to practice something different. So because I just don't like this question that's being asked, I want you to cross off that and write x plus 1, because this is what I feel like we need to practice. Okay, so again, it's not, you shouldn't normally change it, but I want us to practice dividing by x plus 1. So I'm going to evaluate my function. So using x plus 1 as my divisor, x plus 1 equals 0, so we're going to use negative 1 here. So negative 1 to the 79 plus 3 times negative 1 to the 24 plus 5. So the reason why I want us to practice the negative 1 is to remind you when negative signs cancel and when they don't cancel. Okay, so even though this seems like it's going to be a really hard problem because of that 79, it's not, because we get to use this shortcut. So if you have a negative with 79 of negative ones, well, the ones are easy. 1 times 1 times 1 times 1, doesn't matter. It's all 1. All you really have to worry about is it going to be negative or positive. So if you have 79 negative signs, well, an even amount of negative signs, so let me just do a few. An even amount of negative signs, so these pair of negatives, they would cancel each other out, become positive. This pair of negatives cancels out, becomes positive. So you can see every time you get 2 together, they cancel out. Well, if you only have a divisor, if you only have something that's multiples of 2, it's going to be positive. But when you end up with one odd leftover negative sign, it is going to stay negative. Okay, so what that means for us is that this is going to be negative 1. This is going to be positive 1 times 3 will be positive 3. Okay, and then we end up with 2 plus 5, which is 7. So no, it is not, because the remainder is 7. All right, so example 3. Again, why don't you pause it, see if you can do this. So I'll give you pause it, and I'm about to start. So you should have gotten, so for example A, you should have gotten -2. So no. B, you should have gotten 0. So yes. All right. Okay. Example 4. Find all 4 polynomials of degree 5 that have 1, 2, 3, and -5 as zeros. So hopefully you can remember what happens. Like let me just show you one of them. If you end up factoring and you get the factor x minus 1, the point of factoring is to get solutions. So the solution that you get from x minus 1 is x equal to 1. Well, you can go that other way. Okay, so if this makes sense to you, I'm just about to state the opposite direction. So what do I mean? I'm telling you what the solutions are. 1 is a solution, 2 is a solution, 3 is a solution, and -5 is a solution. So x equals 1 is a solution. X equals 2 is a solution. X equals 3 is a solution. And x equals -5 is a solution. So if I take a look at x equals 1 as a solution, it came from a factor of x minus 1. Okay, this came from a factor x minus 2, x minus 3, and x plus 5. All right, now this is a polynomial. It's like a polynomial that's already been factored, but it's a polynomial. And it did tell us to go ahead and leave it in polynomial or in factored form. I won't ask you to FOIL all this. It's just way too much to do that many. So you may be thinking, well, that was easy, we're done. And really, it still is easy, but make sure that you satisfy all parts of it. So read the problem again. It says, find all 4 polynomials of degree 5 with the zeros 1, 2, 3, and -5. So degree 5, that means that you should have x to the 5th power. So if you think about x times x times x times x, we only have a degree 4 here. Now you don't want to just make up another 0. Don't just say, well, let's just put x plus 40 here. You don't get to make up something. Make sure that you don't put even, you can't even add an x here, because if you put an x here, you'd be saying that x equals 0 is a solution, which it didn't tell us is. So that's not okay either. Don't just put something random here. These are the only zeros that we have. So one of them must be a double 0. What do I mean by a double 0? Let me come over here just to show you what I mean. So a double 0, for instance, if I ask you about x plus 4 squared, this is an example of a double 0 because the only solution is -4, but because that factor was squared, it's considered to be a double 0. Graphically, what double zeros look like, they look different than regular zeros. Because how would you graph x plus 4 squared? Well, you would go left 4, and that would be the only transformation in this case. So it would look something like this. This is an instance of a double 0 because your quadratic, it comes down, and then where that hits the 0 is actually the vertex, and then it comes back up. Normally, well, I shouldn't say normally, but normal zeros that only are single zeros, they cross it and continue on, cross it and continue on. Those are single zeros. But if the vertex hits, if there's like a turning point, we call it a turning point because it's headed down, gets to that bottommost point, turns upward. That's a turning point. If it turns on a 0, it's going to be a double 0. And again, it's this square thing that kind of also indicates that it's a double 0. So, applying that idea to our function, what we're going to do is we're going to say, well, one of these guys, must be a double zero. And since the problem didn't tell us which one is a double zero, we're just going to say, well, let's say this one was. So let's say this one was. So I'm going to put a little square here. So now, if you notice, now you would have a degree of 5 because you have x that would get squared. So this is x squared times x is x cubed times x is x to the 4th times x is x to the 5th. So this is one possible solution. And this is why it says find all 4 polynomials, because this is only one solution. Remember, we just picked this one randomly. You could have said, well, what if x minus 2 is the double factor? So that's another good answer. So typically on like a quiz or on a test, I would have to tell you which one because I only want to grade one possibility. But this is just a very general question where I'm just kind of trying to show you that you can have a double zero and this is still only giving you those same 4 zeros. It's just that one of them is a double zero. So it's just kind of a general problem. And that's it for today's lesson. Oops. I'm making that last one the double zero this time. Okay, so those are the 4 solutions, 4 possible polynomials that would have represented, see, this is the root of 1, this is the root of 2, the root of 3, and the root of -5, which in this case happened to be the double zero.